Hi everyone, I'm Liron Faybish, and first I want to thank you all for joining my talk. Today we are going to talk about detecting anomalous sequences using text processing methods. Try reading that sentence. Sounds weird, right? And here's the original sentence I wanted to say. Hi everyone, great to see you all in my talk. These two sentences have the same words, but when changing the order of the words, like in the first sentence, it just looks weird and makes no sense. So detecting anomalous sequences is a common problem, where you need to distinguish between normal sequences and the weird ones. This example is related to text sequences, which are sentences. But there are a lot of types of sequences. Basically, it's any collection of items that are organized in a certain order and that the position of each item has a meaning. You can also think about sequences of actions, system logs, events, and so on. The field we are focusing in our team is information security, and detecting anomalous sequences of events or actions in that field is really important, since detecting changing in the behavior of the users could be critical for the organization, and we need to detect it as soon as possible. So we need to find a way to build a model that will be able to do that separation between the normal and the anomalous sequences. As I said before, I am Liron Faybish. I am a data scientist on PayPal for almost 6 years. I am part of the cybersecurity threat oversight team, which is part of the information security organization. We are a team of security researchers where each one has a different perspective and unique point of view in order to cover as many security issues as possible. My role is finding machine learning solutions for information security problems. In addition, I have MSc in Information Systems and Software Engineering from Ben-Gurion University. So as I mentioned earlier, our goal is detecting anomalous sequences, which means to detect unusual sequences of items or events. For example, if we are looking on those two sentences, where one looks normal and the other one looks weird, we would like to distinguish between those two sentences, and that our model will be able to say that this sentence is a good sentence and the other one is not. In this talk, I'll show you the architecture I used for detecting the anomalies, and I'll talk about the algorithms I used for that mission, which are word2vec, Bert, and Autoencoders. I'll show you how you can use them for building the full architecture, from processing the sequences to detecting the outliers. Later, I'll show you the experiment I made and how you can use this architecture for text sequences and also for sequences of actions that relate to the information security domain. So let's start with the architecture of the method. The architecture I used for that mission included two phases. The first step is modeling the sequences, and the second step is finding the anomalies. In the first step, we would like to create a vector representation of the sequence data. We want to take that sequence of items or events and convert it to some numeric vectors that we will be able to use in the second step. The way I wanted to do so is using text processing methods such as word2vec and Bert. In the second step, we want to take the vector we extracted on the first step and train a model that learns the structure of the good sequences and identifying the anomalies. The model we chose for that mission is Autoencoders. Let's do a quick overview on those algorithms. In the text processing world, the most common algorithm is word2vec. This algorithm is using neural networks to learn word associations from a corpus of text. And as you can understand from its name, each word represented by a vector, such that the similarity between those vectors indicates the level of similarity between those words. Word2vec is also able to capture semantic and syntactic relations. For example, in the words vector space, the relation between king and queen is the same as the relation between men and women. And the relation between big and biggest is the same as the relation between small and smallest. This model is context independent, which means that there is only one vector per word. So different senses of the same word are combined into one single vector. The two models architectures that word2vec utilize are SIBO, continuous bag of words, and skipgram. And the difference between them is that in SIBO, the model predicts the current word based on this context, which is the words next to it in the sentence. And in skipgram, the model is trying to predict the context, which is the words next to it, based on the current word. In Python, there is an implementation of this algorithm in the GenSim library, and you can use it to build a word-to-vec model. Another text processing algorithm is Bert, bidirectional encoder representation from transformers. Bert is a language model that was bidirectionally trained and can learn deeper context from language than single-direction models. Bert embeddings are context-dependent, which means that Bert generates context-aware embeddings that allow for multiple representations of each word based on a given word's context. And since Bert generates contextual embeddings, the input of that model is a sequence, a sentence, rather than a single word. And we can get one vector that represents the entire sentence. Bert was pre-trained in two tasks, masked language modeling, MLM, where we are masking some of the tokens, which are the words, and we are trying to predict them from the context. And the other one is next sentence prediction. We're given two sentences, A and B. The model is trying to predict the probability that sentence B will appear after the sentence A. The full structure of BERT includes transformers, attention, positional encoding, and so on. And it is not in the scope of that presentation, and you can read about it later. In Python, you can use the transformers library for both using the predefined BERT and for training a new one from scratch. Okay, so now that we have a vector representation of the sequences, we can move to the next phase, which is learning the structure of the good data and detecting the anomalies. To do so, we are using autoencoders. Autoencoders are neural networks that use to learn an efficient encoding of unlabeled data. It includes two phases, encoding the data and decoding it. So the final output should be the same or as close as possible to the input. So autoencoders are trying to minimize this reconstruction loss. In order to use this architecture for anomaly detection, we are training the autoencoder on the normal data. So when the model is fully trained, it knows how to encode and decode regular data. And if there is another structure of data that looks differently from the regular data, it would interrupt the flow and the results of the model. So if there is an input of a good data, the reconstruction loss should be low. And if there is an anomaly, the reconstruction loss should be high, because the model was trained on normal data. In Python, in order to build the autoencoder, I used Keras and TensorFlow. When dealing with sequences, there is a unique type of neural networks that's called RNN, recurrent neural networks. So in order to deal with our sequences, we need to build an RNN autoencoder. But the main challenge here is that each sequence has a different length. For example, each sentence consists of different words. So we need to build the autoencoder in a way that it could handle different lengths of sequences. There are a few options to do so. The first option is truncating the sequences into a predefined size, so all sequences will have the same size. But in this option, we are losing data because we are cutting the sequences, and in a long sequences, we are losing a lot of data. The second option is to use padding, which means to pad the sequences, adding zeros or a predefined value in the beginning or in the end of the sequence, in order to make all sequences to be in the same size. But this solution creates long tail of padded values for short sequences, and it can bias the results of the model. So the next option could be using n-gram, which means to split the sequence into few smaller sequences. But the downside of that solution is that we are losing the meaning of the full sequence and the connection between the beginning of the sequence to its ending. So the last option is adding a masking layer, which means to use padding and tell the model that this part of the sequence isn't actually part of the real sequence, and it should skip it when training and testing the model. This solution is a bit challenging, since the structure of RNN autoencoders can't handle the regular masking layer because of its encoder-decoder structure. When forwarding the sequences along the encoder and getting to the middle layer that creates an encoded representation of the sequence, the masking layer is lost during that compression. So there is a need to create a custom middle layer that knows how to deal with masking and forward it to the decoder. It's possible, but it's a bit more difficult and requires some changes in the code. You can read more about using masking in RNN autoencoder after this presentation. In our method, we decided to combine padding, masking, and n-gram, so we will be able to support all sizes of sequences. We are using padding and masking during the training phase, and we are using n-gram when there is a new sequence length in the testing phase that doesn't appear in the training phase, so we are splitting it into a few smaller sequences. Example for using word-to-vec with RNN autoencoder could be as the following. Suppose we are having the following sentence. Hello, how are you? With word-to-vec, each word is represented by a vector, and the sentence is a sequence of vectors. For example, the word hello is represented by the vector 0.1, 0.8, 1.2, 0.5, and 1.9. These sequences of vectors are then fed into the trained RNN autoencoder, into the encoder and the decoder layers, and at the end, we have the reconstruction loss. And if its value is high, it's an anomaly, and if it's low, it's normal. And in this case, since the sentence looks perfectly fine, the reconstruction loss should be low. So at the end, we are having two options. One is using word-to-vec and RNN autoencoder, and the second option is using Bert with regular autoencoder, since Bert can produce one vector per sentence, and there is no reason to use the RNN autoencoder, and we can use the regular one. So now, after talking about the architecture of the method, we can move to the second part of the presentation, which is the experiments I made in order to prove the accuracy of both methods. In order to test both methods, we did the following test that uses text sequences as input. We used a dataset that contains tweets about the Avengers Endgame movie. This dataset is taken from Kaggle, and you can find it online. We just needed to clean it a bit, remove hashtags and such from the original text. In the first scenario we used word-to-vec and RNN autoencoder. So we split those sentences into train and test set, and we trained a word-to-vec model on the train set. And in the word-to-vec space, each word in the dataset is represented by a vector. For example, the word Thor is represented as the following vector with 10 values. Another example of word-to-vec vectors is that if we are looking on the vectors of the words Thor, Iron Man, Loki, Widow, and Captain, we are seeing that their vectors are found close to each other since all are characters in the movie. And the vector of the words hammer, sword, glove, weapons, and blade are also found close to each other since all are type of weapons. So after training the word-to-vec, we need to train the RNN autoencoder. So we are taking the output of the word-to-vec, which are the encoded vectors, the sequences, and we are building the RNN autoencoder. And after training the model, we have a reconstruction loss for each sequence. So in order to test the full architecture of the word-to-vec and RNN autoencoder, we created three types of sentences. The first sentence is the original sentence. For example, Avengers Endgame is a masterful epic, a true culmination of 22 films that not only concludes the story, but expand upon it, and wow, what an ending. So that would be our first sentence. The second sentence is the same sentence, just the words are shuffled. And the third sentence is half the same as the original sentence, and only its second half is shuffled. We gave the model those three sentences, and we calculated the reconstruction loss. As you can see in the histogram, the loss of the original sentence was lower than the other two sentences, the shuffled and the half shuffled, which means that the model was able to identify the original sentence and separate it from the anomalous sentences. So we did the same experiment with 1,000 sentences, and we calculated the loss compared to the original sentences. We considered four scenarios. Sentences consist of random words, sentences consist of half real sentence and half random words, the same sentence but shuffled, and half real sentence and half shuffled, and we calculated the AUC. The AUC for the first scenario was 90, for the second scenario it was 87, for the third scenario the AUC was 86, and for the last scenario, which is the closest as possible to the original sentence, the AUC was 75. So we also wanted to test this dataset using the Bert architecture. We used the pre-trained Bert model and tokenizer using the following code, and we took the output of the Bert model, which is 1 vector per sentence, and we built a regular autoencoder for the anomaly detection phase. Bert tokenizer is working as follows. Each sentence is converting to a list of tokens that represents the sentence. It's not necessarily that each word is represented as a token, since Bert worked with subwords and can split one word into few tokens. The first token is the CLS token, which is the classification token, and it's there to represent the sentence level classification. And the last token is the sep token, which is the separation token that uses to separate between sentences. Later, those tokens are the input to the Bert model, and its output has two parameters, the last hidden state and the puller output. The last hidden state is the sequence of hidden states at the output of the last layer of the model, and puller output is the last layer hidden state of the first token of the sequence, which is the classification token, after further processing through the layers used for the auxiliary pre-training task. For our task, we are using the puller output as the vector representation of the sequence. And now we have one vector representation per sentence, and that would be the input for our autoencoder. So now we have our Bert model and the autoencoder that generates the reconstruction loss, and we can move on with our experiment. And if we are going back to our experiment where we tested different types of sentences, so here we tested 3 out of the 4 scenarios we used in the previous experiment. We ignored the fully random sentences because we felt it was too easy for the model and doesn't reflect our mission. So we tested the half real sentences and half random, the shuffled sentences, and the half real and half shuffled sentences. The AUC was 90 for the half random sentences, 88 for the shuffled scenario, and 80 for the half shuffled sentences. And compared to the word-to-vec method, in this case with the Avengers Endgame tweets datasets, Bert with regular autoencoder was outperformed the word-to-vec with RNN autoencoder. So that was an example with text sequences. But what if we had a scenario of other type of sequences? So now after testing this architecture with text sequences, we can move to the real reason I created this architecture, which is detecting anomalous sequences that relates to the information security domain. And in this case, it's sequences of actions. So the next scenario is related to the information security domain, and this is the most interesting part of our research. We have a system where we have accounts and users, and the users can perform actions on the accounts. For example, actions like login, logout, change details, see the account details, and so on. Let's say that session is a sequence of events from login to logout. So we want to be able to detect a user who performs anomalous sessions and doing weird sequences of actions on the system. Each action by itself is okay, but an anomalous sequence of actions could be dangerous, and it is critical to the organization to detect those sequences on time and prevent unauthorized actions. In this case, the method we chose is using word-to-vec and RNN autoencoder, and the reason we chose this method is because it was the first architecture we thought about, and only later we thought about using Bert. So for training the word-to-vec model on the sessions dataset, we model each action as a word, and a sequence of actions was a sentence. We fed those sequences into the word-to-vec model, and the sequences of vectors are fed into the RNN autoencoder. So now we have a reconstruction loss for each sequence, and that score can indicate how normal or abnormal a session is. We trained the data on 30 days of sessions and we tested it on 7 days. We also have examples of 2 bad actors who we know for sure that performed bad sessions on several accounts, and we wanted to see the scores the model gave to those real cases and if the model was able to separate those scenarios from the rest of the data. So we calculated the reconstruction loss for the test set, and we plotted the results on the following histogram. So this is the histogram of the reconstruction loss on the test set, and if we are doing zoom in from 0 to 1, we are seeing that most of the results have a loss between 0 to 0.2. Okay, so that's the loss of the test set, but what does it mean? Now let's look on the histogram of the first known bad actor, which we know for sure that performed bad sessions on several accounts. Its distribution looks almost the same as the test set, but if we are focusing on the highest values, we are seeing some interesting results. So if we are focusing on the sessions with the highest loss, and we are investigating those accounts, we see that those accounts indeed were involved with bad behavior. We starred those accounts, so different accounts got different colors. And as you can see, almost all of the sessions with a reconstruction loss above 0.2 was bad accounts, which means that those sessions were indeed anomalous, and the model was able to tag them as anomalies and identify that their structure was different from the rest of the sessions. So now let's look at the second bad user, and again, also in this case, almost all of the sessions that received a loss above 0.2 was related to bad accounts. This means that our model indeed was able to recognize the anomalies sessions again. And if we are looking back in the test set and putting a threshold of 0.2, we are staying with around 5% of the results. Of course, that since the size of the dataset could be really big, it isn't enough to filter out 95% of the results, because we are still staying with a lot of events to check. But if we are adding more constraints on the sessions, like if the type of the actions are sensitive, or if we are looking on the user's history or the account history, or if we are combining this method with other alerts, we can reduce the results and the false positive rate even more. So now we have a system that gets us input all of the actions that has been made on the accounts, which are the sessions we mentioned earlier, process it through the model, and generate a score for each action, for each session. This score indicates how normal or abnormal this session is. And according to the threshold we are setting based on the results of the model, we can decide if this session is an anomaly or not. If the score is above that threshold, it's an anomaly, and if it's below that threshold, it's a normal session. Our first next step will be testing the sessions dataset with the Bert architecture and compare the results with the word-to-vec ones. Later, we can also use this architecture for other tasks. For example, we can extract features for each sequence and use it for other tasks like classification or clustering, and learn more about the connection between the sequences. For example, we can cluster the sessions we talked about into several clusters and see which users are acting alike and maybe create new collaboration between them. So for conclusions, we talked about how we can detect anomalous sequences, that their structure looks differently from the other sequences. We saw how we can use text processing methods, such as word-to-vec or Bert, in order to create features vectors out of the sequences. And we also showed how we can use autoencoders, both regular and RNN, for learning the structure of the good data and detecting the outliers. We demonstrated this architecture on both text and non-text datasets, and we showed how we can train the model on both fields, and how the model indeed was able to detect the outliers in both cases. Thank you for listening to my talk. If you have any questions, please feel free to reach out to me. Thank you.
Great. Thank you, Liron, for the very, very nice talk, and thank you for leaving some time as well for the Q&A. So the audience members who are participating in chat and viewing it, feel free to leave your questions in the comments. I'll be moderating them and also service it to Liron.
Okay, I'll do it. Just to see I'm seeing the chat, okay. To see the chat, and I'll try to answer
That's right.
the best I can.
That's right. That's right. So let me help you with one. So there's a question by in the mirror. I will bring it up on screen so that we can have a look. How do you determine the threshold when actually deploying these models? It was 0.2 in a test set. Like, when is a sequence labeled as anomalous at inference time just based on these two observations?
Okay, since the field I'm working on in PayPal, I can't tell too much because it's still information security, but basically the threshold is, I'm defining the threshold based on the data sets and based on the sensitivity of the data. Like, I'm talking to the team who's responsible on the alerts, and like according to their comments, we are setting the threshold. Because if it's too sensitive, we want to set the threshold lower so we get more alerts. But if it's not that sensitive, we can create a higher threshold so we get less alerts. So basically, it's just testing and seeing what's the best threshold. We just play the threshold according to the type of the dataset.
Yeah, all right, nice. So it's some sort of a heuristic method to make sure you get the kind of
yeah, in this case,
accuracy.
that in the presentation, I said like explicitly it's 0.2 in this case, just to make it clear to the audience. But of course, it's not like explicit threshold. Like we can say put the threshold around 5% of the results. So we can put the threshold with 2% of the results. And again, we're playing with the threshold.
Okay, very nice. Thanks for that. There's a second question which I'll bring up on screen by Marc-Antoine Parent. Curious about the article on RNN masking.
Okay, I'm not so sure I have a good answer for that except Google it. Because it's a bit tricky to use masking with RNN. So just Google using masking with RNN autoencoders, and I think the top 5 results will be a good answer for him.
Yeah. I think it's worthwhile moving the discussion over to Discord, and if anyone else has come across this article that we can share, then that would be useful as well. So we still have a couple of minutes left. There is another question, which I'll bring up on screen as well, by Morgan Mahood. What does a good actor look like?
I'm guessing this question is regarding the second experiment I made. I have no good answer to say how a good actor looks like because I'm working with another team that gave me a bunch of good users so I can build a model on. If we are talking about text datasets, a good actor, like a good sentence, is just a normal sentence, and I created the bad users, the bad sentences. And if we are looking on the second, like the information security experiment, I'm working in a company where we have those examples, and I can't share too much, but I worked with a team and we're working together on those data, and they gave me the data, and I'm not so sure I can say more than that.
Yeah. I guess it's a very domain-specific definition of what a good actor would be.
Definitely domain-specific.
Yeah, excellent. All right. Thank you for that answer. Are there any other questions? You probably have like 1 more minute remaining before we can conclude. I guess there's a good place to stop. If anyone else has any questions, please hop on over to Discord and you can ask your questions there. Liron, hopefully you're also on Discord, and then you can have some nice discussions about these on the channel over there.
Yeah. All right, thank you for hosting me.
Yeah, thank you very much for your talk.